Okay, good morning again to everybody. Today we will introduce some of the most basic techniques for performing an asymptotic expansion of some wave field. As you may remember, last time we saw one example of an asymptotic representation of a wave field, that is the Lüneburg-Klein asymptotic series, that was directly obtained from the wave equation, either in a scalar form and then in a more complex way for the full vectorial electromagnetic field. Today we will use a different approach because we will not start from the wave equation, but rather we will start from an integral representation of the wave field, which is something very common indeed in applied electromagnetics, for instance, because in many occasions our solutions of Maxwell's equations are available not in a closed form, but in the form of some kind of integral, either a spatial integral or a spectral integral. Remaining to spatial integrals, the most basic example is that of the so-called radiation integrals in free space, or also in bounded environments, by which you can express your wave field, for example, the electric and magnetic field produced by an impressed source, like this impressed current Ji here, by writing the field as a superposition integral, in which the integrand is constituted by the product of the known impressed current and a kernel, an integral kernel, which is by definition the Green's function of the problem. For example, if we are in free space, we may use the simple scalar Green's function for Helmholtz equation in a time harmonic regime. Whereas if we are in a bounded environment, so you can imagine now the currents are not located in free space, but for example inside a box. And on the boundary of this box, on the walls, some kind of boundary condition, like for example the condition of a perfect metal, or some impedance boundary condition, which may model an imperfect metal, can be enforced. It is possible, if the geometry of the box is simple, to find out the Green's function also in this bounded environment. In this case, it will not be a scalar function, but it will rather be a tensor or dyadic Green's function. But anyway, we are able to write the electromagnetic field again as a superposition integral. Another example is that of using not primary but secondary sources, which is something typical of diffraction problems. For example, if you have a slit in an opaque plane, like a metal plane, and you illuminate from the left side this plane, this slitted plane, with, for instance, a plane wave, then what happens is that part of the radiation goes through the slit, and therefore it produces an electromagnetic field on the right side. Now, this scattered or transmitted field can be found in terms of secondary sources by means of the well-known equivalence theorems. You can, for example, replace the slit with a metal, so you obtain a continuous unslitted plane. But where the slit was present, you must introduce some fictitious secondary sources, like, for example, magnetic equivalent surface magnetic currents, in terms of which then we are able to write the electromagnetic field, which is scattered on the other side. For example, if here the boundary is a perfect plane, an infinite plane, then by symmetry we may double the secondary sources and just use the free space Green's function, for instance. In any case, what matters is here, to motivate this lesson, is that we are able to write down our field in terms of an integral. Now, this integral typically cannot be evaluated in a closed form. It may be evaluated numerically. However, again, for simplicity and also for physical insight, it may be more useful, if possible, to resort to some kind of asymptotic expansion, which will be typically a high-frequency asymptotic expansion. So we will have a large parameter, which is the wave number or equivalently frequency. Okay. Okay, having said that, we have finished with the physics today, and now we will delve into mathematics. Let us start with one important class of integrals, which you may encounter in practice, the so-called Laplace-type integrals, whose name comes from the prototype, the Laplace transform, which you all know is defined by this generally improper integral, the integral from 0 to infinity, with respect to the real variable t, of the product of our function f of t, which is a general function, times the exponential e to minus st. Now, generally, this is an improper integral. Sometimes it may be a converging integral, so the integrand may be integrable in a Lebesgue sense. And as you know, typically, in order to have this integral converge, then the real part of the variable s, which is in general complex, must be larger than some smallest quantity, which is called the abscissa of convergence of the Laplace transform. Okay, so typically Laplace transforms are functions of the complex variable s defined in a half plane. And it is possible to prove rather simply by using Morera theorem, which we proved in our second lesson, that Laplace transforms are holomorphic functions within their domain of definition. Okay. Now we will deal with a sort of generalized Laplace-type integral in which we may relax the boundaries, so they are not necessarily 0 nor infinity, but they can be two arbitrary numbers, a and b. And in addition to that, instead of having t in the exponent, we may have a function phi of t. So here you can see this integral is defined in terms of two functions, f of t and phi of t, where both are real, and we will assume they are sufficiently smooth, for example, differentiable, whereas k is a real parameter, which we will assume is a large parameter. For example, it may be a wave number, in which case we are performing a high frequency asymptotic expansion of this integral. The integral is indicated as is usual by the letter I, and it is a function of this large parameter k. What can we do with this kind of integrals? Well, the intuition, which is on which the asymptotic evaluation is based, can be grasped from this example in which we integrate from 0 to b. Now, if you let k tend to infinity, you may see that the exponential function here tends to 0 for any value, positive value of t, okay, in the limit when k tends to infinity, because we have a negative sign in the exponent, with only one exception. The exception is when t is equal to 0, because when t is equal to 0, then the exponential is exactly equal to 1, regardless of the value of the parameter k. So the idea is that when k is large, this exponential is negligible everywhere except in a small neighborhood of the point t equals 0. So that's the only part of the integration domain that matters, as long as you're interested in the asymptotic limit when k is large. So the idea is that the global asymptotic behavior in this limit is related to what happens close to the origin of the t-axis, so to the local behavior of the integrand. Okay. For example, take this function j of k, which is the integral from 0 to infinity of 1 plus t times the exponential e to minus kt, and integrate by parts. Now you will discover that this integral can be done analytically, and the result is 1 over k plus 1 over k squared. So here we don't need to do any asymptotics. This is exact, okay? But it's an exact result which is in the form of the first two terms of an asymptotic expansion in inverse powers of k. However, you could, by adopting the approach outlined here, so isolating what happens close to the origin, then you could neglect this term t here inside the brackets, because it's negligible when t tends to 0 with respect to the constant 1. And then you may just integrate from 0 to whatever upper integration limit you may choose r of the exponential alone, which again can be done in a closed form as an integral. And the closed form result is this one, which in the limit when k tends to infinity becomes simply 1 over k. Now, as you can see, this is not the exact solution, but it is asymptotically correct because it's the lowest order asymptotic term in the exact expansion. So considering only what happens close to the origin captures the correct high frequency or high parameter, large parameter, let's say, asymptotic behavior. Now, this is the basis. So we expect that something similar occurs in our generalized Laplace integrals. However, in this generalized Laplace integral, in general, we have a function phi of t in the exponent. So what we may expect is that the important points for the asymptotic analysis are those points where the function phi attains its minimum, because at those minima, the exponential is larger than at any other point in the integration domain. Okay, because of the nature of the exponential, which has a minus in the exponent. So the larger is phi, the more negligible is the exponential when k is large. Okay. Okay, let's see how to do that in practice in exact terms. We will distinguish two cases. When the minimum of the function in the exponent phi occurs at one of the boundaries, for example, when it is monotonically increasing, the minimum occurs on the left boundary, okay, like in this picture on the left. Whereas in other cases, our function phi will have an inner minimum. So it's an internal point inside the integration interval, okay? We will distinguish those two cases because the treatment is a bit different. It's simpler on the left, and it's a bit more complicated on the right. Okay, so we will start with the simple case, the case when phi is monotonic. Okay, so the major contribution to the asymptotics is expected to come from the endpoints, either A or B, depending on the function phi. Okay. Let's see how to proceed. The simplest case we may find under the assumption that phi is monotonic is the case when the function f, which I remind you, is the function that multiplies the exponential function in the integrand. Okay, so the simplest case is when our function f of t is a smooth function, because in that case, integration by parts is the technique that allows you to find the asymptotic expansion of the integral. For example, take this function I of k, defined by the integral on the right-hand side, again from 0 to infinity. We have the exponential e2 minus kt, and the function f is the inverse of the square of 1 plus t squared, which is a smooth function on the real axis, okay? It's infinitely differentiable, no singularities, no discontinuities. So if you perform an integration by parts, you find the antiderivative of the exponential, which gives rise to this term here, the exponential over minus k, and you keep the other term, the function f, unchanged. Then this must be evaluated at infinity and at 0, the boundaries. Then there is the second term in the integration by part procedure, which is an integral from which you can extract out the factor 1 over k, which does not depend on t. And then what remains inside the integral is what you can read here. And this second addend can be estimated quite easily, because you can, by exercise, find some way of finding an upper boundary for the integral, from which you will discover that this second addend is of the order of 1 over k squared. And being of the order 1 over k squared, it is negligible, so it's much smaller than the term 1 over k, which comes from the finite part here. So we have found the first term in a high-frequency asymptotic expansion. If we were interested in the next terms, we could proceed again integrating by parts. So we iterate the procedure. And so now we can state the theorem which covers this case. So phi monotonic f of t regular. The theorem is the following. Suppose that our function f of t is smooth in the sense that it possesses n plus 1 continuous derivatives, whereas the n plus 2 derivative exists, but is only piecewise continuous. So it may have some isolated discontinuity inside the integration domain from A to B. Then you can prove, integrating by parts, that the following asymptotic representation holds, in which you have n+1 terms. This is a development in terms of inverse powers of the large parameter k. You can see the exponential here, evaluated at the boundary where your function f, your function in the exponential is smallest, so the lower boundary a, and then the derivatives at the same boundary of the function f. So again, what happens at the lower boundary determines the asymptotic behavior when k is large, okay? According to the intuition presented before. So this theorem covers Laplace-type integrals. The Laplace transform is the particular case when the lower limit is equal to 0 and the upper limit is equal to infinity. However, this can be generalized quite easily. The first generalization is that you can let the upper limit go to infinity, so actually this covers also the Laplace transform. However, you should only assume, in addition to the other assumption on the function f, that the function f does not grow too fast to infinity as t tends to infinity, because otherwise the integral would not be defined. So, for example, if the function f is bounded in a neighborhood of infinity, everything works, because then the exponential guarantees the convergence of the integral at infinity. But you can also admit that your function f is of the order of an exponential function e to alpha t, with alpha a real constant, because then this integral, the Laplace integral, will be defined for sufficiently large k, according to the definition of convergence abscissa of Laplace integrals, okay? So the class of functions f which is covered by this kind of theorem is quite large. The other important generalization is that you can have an exponential function which is more general, in the sense that instead of having the integration variable t in the exponent, you can have a function phi of t. However, this function must be monotonic, so that we are in the case we are discussing here on the left. For a monotonic function, again, everything is concentrated on the boundary where the function has its minimum. So in this case, why it is easy to generalize the theorem to this case? Because it's a simple matter of changing variables in the integral, and then recovering the case of the covered by the theorem. Okay, so you introduce a new variable tau, which is equal to phi over t, and by doing that and performing the necessary steps, the algebraic steps, you will be able to write down this generalized Laplace integral in terms of an ordinary Laplace integral. Okay, and so be able to apply the theorem. Mm-hmm. Well, because if phi is not monotonic, then there will not be a one-to-one correspondence between the integration domain a, b in the original variable and the new integration domain. Because if the correspondence is 1 to 2, for example, you can imagine a point in the codomain here comes from two different points in the domain, which is something problematic when you change variables. So if you change variables, you wish to have something like that. So there is a one-to-one correspondence between parameters, okay? In addition, if you have a situation like this one, in which you have an internal minimum, then the logic changes, because the logic is that the minimum dictates the asymptotic behavior. So if now your minimum is inside, you should do something different, as we will see in a moment. But before addressing that case, we will remain for a while in the case where phi is monotonic, because we will cover the situations in which the function f is not regular. It's not enough regular. Let's see what may happen when f is not sufficiently smooth. Now, the problem may occur when the function f is not sufficiently smooth at the lower boundary, because as we have said, it's the local behavior close to the lower boundary that is important. The upper boundary can be neglected, it can be changed as will. However, it may happen that the function f is not sufficiently smooth at the lower boundary. For example, take this integral from 0 to 5 of this function, which is a polynomial up to -1/2 times the exponential function. Now, if you try with integration by parts, which is the simplest asymptotic technique, so it's the first thing to try usually, then you will discover that the finite term, the one here in square brackets, actually contains the term t squared plus 2t to -1/2, and this term, being the inverse of a square root of something that goes to 0 as t tends to 0, this is singular at the lowest boundary. That is, if you try to enforce t equals 0 here, you will find infinity, which is nonsense. Okay, so you cannot integrate by parts. That's because you have an exponent, a negative exponent here of something that goes to 0 at the lowest boundary. Note that even though the function here is singular, however, it is integrable because it's a weak singularity. So a 1/2 singularity is integrable in a neighborhood of the origin. So this integral is well defined. The problem is that you cannot evaluate it by using integration by parts. So what can you do? Well, you can reason like in this slide. We have said that what matters is a neighborhood of the origin. So the upper integration limit, which was originally 5, is not so important. You can change it at will. And so, for example, you can take it to be less than 2. Why exactly this value? Because if r is less than 2, then we are within the circle of convergence of the Taylor expansion for this square root function. So, by performing a little algebra, you can first factor out this term here, 2t to -1/2, and then you remain with this kind of thing, 1 plus t over 2, again to -1/2. Now, since t is a small quantity, because we are interested in the local behavior close to the origin, then we may expand this function using the Taylor series, and you will find that the lowest order term in the Taylor series representation of this function here is 1 minus t over 4. So you end up with these two terms here, which can be inserted inside the integral, giving rise to these two contributions. In the first one, you have the integral of 2t to -1/2 times the exponential, and in the other one, you have 2t to +1/2 over 8, again times the exponential. So you have the same pattern, a power of the integration variable t, some constant, some numerical constant, which does not matter, and then the exponential function. Now, this can be evaluated in terms of known functions if we replace the upper integration limit by infinity, which, note, is not permissible strictly because the radius of convergence of the Taylor series that is not infinite, it's bounded. However, this does not matter from an asymptotic point of view, because the error that you introduce by extending the integration domain to infinity, so beyond the circle of convergence of the Taylor series, is exponentially small, so it's negligible with respect to the any term of the asymptotic series. What's the use of extending the integration domain to infinity? Well, the use is that now the integral extended to the positive real axis of t to some power times the exponential is by definition the gamma function that we defined in one of the previous lessons. So we are able to express those integrals in terms of the gamma function. In particular, in this example, the first integral is expressible in terms of the gamma function with the argument 1 over 2, whereas the second integral is the gamma function with the argument 3 over 2. And then there is the large parameter, which comes out by simply performing changes of variables in those integrals. And so you can see in the denominators the powers of k, which are 1/2 and 3/2. And so this is the asymptotic representation, the first two terms of an asymptotic representation of our integral I of k. Okay. Here at the bottom you have, as a reminder, the definition of the gamma function, which is in general a function of a complex variable defined in the right half plane of the complex plane. Okay, but here we use the gamma function with real arguments, so it's enough to consider it as a function of a real argument. Okay, this example leads directly to Watson's lemma, which is the generalization of what we have just seen. So basically what we have done is we have replaced our function f with its asymptotic development, valid in the limit when the integration variable goes to 0. Okay, because 0 is the only point that matters asymptotically. The other assumptions are that the function f is integrable in a neighborhood of the origin, and it is not too fast growing at infinity, because otherwise the integrals would not be defined. If we know an asymptotic expansion of the function f in a neighborhood of the origin, like this, and as you can see, there are coefficients a sub n and powers t up to lambda n minus 1, where those numbers lambda n are ordered, so lambda 0 is less than lambda 1, which is less than lambda 2, and so on, okay? So they are increasing powers of the variable t. Then if you replace these inside the integration domain, you extend the integration domain up to the entire positive real axis, as we did in the previous example. By doing all that, you come up at the end with an asymptotic expansion of our integral I of k, in which the coefficients a sub n are here. In the numerator, you have the gamma function evaluated at the numbers lambda n, and in the denominators, you have the powers of the large parameter k, where the exponents of k are again those numbers lambda n. Okay? This is a very powerful lemma, and we will see its application in a number of situations. Actually, with the same assumptions, you can extend everything in the complex plane. So you can even let the large parameter be a complex variable z, whose absolute value tends to infinity. So again, we are interested in the asymptotic limit when the absolute value of the argument here goes to infinity. However, you must bound the argument of the z variable strictly in the right half plane. So here you can see that the argument in absolute value must not be larger than pi over 2 minus delta, where delta is a positive number. So we are strictly inside an angle whose internal angle is less than pi. Okay, can you visualize it? So with these boundaries, within these boundaries, everything works, and the Watson's lemma is able to give you an asymptotic expansion in terms of the complex variable z, which is here in the denominator. Okay. Now we go to the other case, the case in which phi has instead a local minimum in some internal point. So again, in this slide, you can see we are in this situation. So now we have a simple local minimum here, and let's see what happens in this case. There are a variety of situations which may occur depending on the order of this minimum. The simplest case is that we have a simple minimum, which means that at the point C, which is strictly internal to the integration domain, the first derivative of phi is equal to 0 because it's a minimum, but the second derivative is different from 0, and in particular it's positive, otherwise it would be a maximum. Okay. There could be higher order minima, so you could have the second derivative also equal to 0, the third derivative equal to 0, okay, but the logic does not change too much. Only the mathematics is a little more involved. Now, let us also assume that the first derivative remains different from 0 at any other point, except then at the minimum. And also that everything is sufficiently smooth, so we don't care about possible singularities. We don't need to care about singularities. Now, since the point C is the point that matters asymptotically, then we expand everything in the neighborhood of C. So, for example, the function f of t can be expanded in a Taylor series close to C with initial point C, and in this Taylor series we take the only zero order terms, so we evaluate the function basically at the point C. Okay, so this is a constant which could be brought outside the integral. Instead, in the exponential function, we do something a little more refined. We keep the first three terms in the Taylor series, the term of order 0, which is phi of C, the term of order 1, which is missing because it's equal to 0, because the first derivative is 0, and then the term of order 2, which is, of course, 1/2 of the second derivative, evaluated at the point C, times the second power of the increment t minus c. Okay. What do we do with this? Then we change variables, of course. So we obtain a simple Gaussian integral e2 minus tau squared, where tau is defined like in this equation. And of course, if you do the change of variables from the differential, you will find out that a factor comes out of the integral, and so you have this denominator here. Once you have done that, the last step is to extend again the integration domain to the entire real axis, which is something asymptotically correct, because the error you introduce is again exponentially small with respect to what you are obtaining. In particular, this Gaussian integral converges exponentially to pi, as is well known. So if you plug this pi into this expression, you will find out the final formula for evaluating asymptotically a Laplace-type integral when you have an internal minimum. This is the formula of the so-called Laplace method, in which you see you have the function f evaluated at the point C, you have the exponential also evaluated at the point C, but in addition, and directly coming from the change of variables, you have this square root in which you have the term pi, which, by the way, should be, yes, here this pi should be pi to 1/2, because the Gaussian integral is equal to pi to 1/2. That's a typo. And that's this pi here inside the square root, and everything else comes from the change of variables. So in particular, the dependence on the large parameter, the algebraic dependence 1 over k to 1/2 comes from the change of variables. This is written formally here. This is the so-called Laplace method. If you have a function phi whose first derivative is equal to 0, but the second derivative is positive for some internal point C, and the first derivative is different from 0 at any other point, and your functions are also smooth, for example, phi is of class C4 and f is of class C2, to stay sure, then if C is an interior point, you have the formula we have just described. And in addition, it can be proved that the next term in the asymptotic expansion would be of the order of the exponential e2 minus k times phi of C, the minus is missing, but it should be there, over k to 3/2. So the complete asymptotic expansion has a first term which goes like k to minus 1/2 here, then k to minus 3/2, and so on. Whereas if C is an endpoint, which may happen because you could have an endpoint with a zero slope, then in that case the formula is this one, which is the same, up with the difference that there is a factor 1/2, which one may guess because you only have 1/2 of the integration domain. But the other difference is that the next term is not like in the first case k to minus 3/2, but it's 1 over k. So the complete asymptotic expansions goes in steps of k to 1/2, okay, instead of steps of k. So it's a slower kind of growth in the powers of the large parameter k. Now, an important remark is that this procedure is actually capable of giving you the complete asymptotic expansion. So the main idea in the proof is that in the proof of the Laplace method is that you should split the entire integration domain into half open integrals on the left and on the right of the minimum point C. On each of those, phi is monotonic, because by assumption our first derivative was different from 0 at points different from C, so that by suitably changing variables on those half integrals you may use Watson's lemma. Okay, for example, in the right half integral from C to B, if you change variables and you let tau is equal to phi of t minus phi of C, so you get this simple integral here. This is the required steps. These are the required steps, and to this kind of integral, then you can apply Watson's lemma. Now, Watson's lemma is powerful because, let us take it again, if you know the complete asymptotic expansion of the integrand close to the origin, then you get the complete asymptotic expansion of the integral when the parameter is large. So Watson's lemma basically gives you a route to determining a complete asymptotic expansion. So not the only lowest order terms, but in principle also all the other terms. And an application of this will be seen in the next lesson when we will apply Watson's lemma to proving the so-called steepest descent method. Now, let me see. Now I would do a short break, and then we will start over with Fourier integrals in the second half, okay? So see you in 10 minutes. Okay, we are ready to start again. Okay, first of all, before leaving the subject of the Laplace method, we may extend it a little bit. For example, Laplace method can also be used when the function f vanishes or it becomes infinite in the neighborhood of the point of the minimum point. Take, for example, this integral from 0 to 5 of the sine function of s and the exponential in which you can see minus k, the fourth power of the hyperbolic sine of s. Now, this is asymptotic to an integral in which you can change the upper integration limit as you wish, and in which you have replaced the sine function with its lowest order power in its Taylor series representation, and you do also the same in the exponent. So instead of the hyperbolic sine, you simply write s, the argument of the hyperbolic sine. If you now change variable, so letting t equal to s squared, you have this 1/2 factor here. The integration domain goes from 0 to the square root of r, and here you have e2 minus kt squared, which again can be written by changing variables in terms of the gamma function, where now tau is equal to kt squared. And in the end, you will find this expression in which you see that our integral goes to 0 as the inverse power of the square root of k. Okay. In this second example, instead, our function goes to infinity in the neighborhood of the origin, because here we have in the denominator the square root of the hyperbolic sine of t, which goes to 0 when t goes to 0. Now, again, with a change of variables, you can reduce everything to this gamma function type integral. And again, you can obtain the correct lowest order asymptotic expansion. So everything works as long as the integrals are defined. So the singularity is sufficiently mild that the integrals are defined in a neighborhood of the origin. And as a final example on the Laplace method, we will derive the classical Stirling approximation of the gamma function, that is, the approximation of gamma of k plus 1 for large and real values of the argument k. The definition of the gamma function is recorded here. Now, one thing one could try to do in order to apply Laplace method is to write the power t to k as an exponential, in which the exponent is k times the logarithm of t. And so we could try to recognize the pattern of the Laplace method in which the function f is the exponential e2 minus t. The large parameter is instead multiplies the function phi, which is now the logarithm of t. However, if you try to do that, you will discover that actually the maximum of phi occurs at infinity, where ft, however, decays exponentially to 0, which is quite critical because a function decaying exponentially is not in the framework of Watson's lemma, in which you should have an asymptotic power series. So now the correct thing to do is to collect everything in a single exponential function, e to k logarithm of t minus t, and consider then the derivative of the entire exponent and let this derivative equal to 0 in order to find the minimum. You will discover that the minimum is obtained at the point t equal k. So now the point where you have your minimum depends on the large parameter. It's a movable minimum, because in a sense, because k is a parameter which is allowed to vary. To avoid this movement of the minimum, it is enough to change variables. So if you let now t equal to ks, of course, now the minimum will occur when s is equal to 1, which is a fixed point in the new integration variable. If you do this change of variables, what happens is that you can factor out this term, k to the k plus 1 power, And you get something which is exactly in the form of the Laplace evaluation of integrals, in which the function phi is now equal to s minus logarithm of s, and the function f is simply equal to the constant 1. Once you are in this situation, having a fixed minimum at s equal 1, where the function is equal, phi is equal to 1, the first derivative is of course equal to 0 because it's a minimum, and the second derivative is equal to 1, and so therefore you have a minimum, and a simple minimum. Then we can use the standard formula of the method and find the final result, in which you will discover that the gamma function of argument k plus 1 is asymptotic to the square root of 2 pi k times the kth power of the ratio k over e, which is the well-known Stirling Laplace approximation of the gamma function, or in particular of the factorial, since gamma of n plus 1 is equal to n factorial when n is an integer. Okay, now let us consider the other family of integrals we are discussing today, the so-called Fourier-type integrals, which of course come from the prototype, which is the Fourier transform, which is not a function of s, of course. This is a typo, it's a function of omega, and in which the kernel now is again an exponential, but with a purely imaginary exponent, as long as t is a real variable and omega is also a real variable. We will generalize this to integrals as in the box, where the integration limits can be arbitrary, and the exponent contains an arbitrary function phi of the integration variable t. Okay, so again, we wish to evaluate asymptotically these for large values of the parameter k. Well, first of all, let us establish a basic fact, fundamental fact of the theory of Fourier transform, which is known as the so-called Riemann-Lebesgue lemma. The basic fact is that any Fourier integral goes to 0 as k tends to infinity. So any Fourier transform must go to 0 when its argument goes to infinity. So, for example, if the Fourier transform is the spectrum of a signal, and so its argument is frequency, when frequency goes to infinity, the spectrum must go to 0. Why is this true? Well, because the intuition is that when the parameter k becomes large, then the exponential inside the definition of the Fourier transform, which is an oscillating function, oscillates so fast that there is a lot of cancellation between the higher and lower parts of those oscillations, which are self-canceling. Now, one can prove rigorously the following, that in the limit when the parameter k tends to infinity, the integral, the Fourier integral, goes to 0, provided that the integral of the absolute value of the function f exists. So that's an L1 function. The function phi is continuously differentiable in the integration interval, and in addition, phi must not be constant on any subinterval of the integration domain. Okay. Now, having said that, how to develop an asymptotic evaluation of Fourier integrals? Well, as I said, there is cancellation in the limit when k is large. So what we expect is that if you consider a point, let us call this point C in the integration domain, and if the derivative of the function phi in the exponent does not vanish at this point, then you can expect that in a small neighborhood of C, that mechanism of cancellation that I mentioned before occurs. And so therefore that neighborhood does not contribute much to the value of the integral. However, if the first derivative of the function vanishes, so we have a stationary point, then this cancellation does not occur, at least in a small neighborhood of the point of stationarity. And so therefore, we can expect a dominant contribution to the asymptotics. This is the logic of the so-called stationary phase method, as we will see in a moment. But again, as we did for Laplace integrals, we will distinguish two cases in our discussion. The first and simplest case is that in which the function phi is monotonic, and in this case the major contribution to the asymptotics comes from the boundaries, as we saw previously. And then we have the case when we have a proper stationary point inside the integration domain, and in that case we will get to the method of stationary phase. If the function phi is monotonic and the function f is regular, we can proceed exactly as for Laplace integrals. So we can integrate by parts, and we can do that a number of times. That depends on the smoothness of the function f. In particular, if the function f has n+1 continuous derivatives with the n+2 derivative, which is allowed to have some discontinuity inside the integration domain, then integrating by parts, you will get this formula in which you can see the terms express increasing powers of the large parameter k in the denominator, and inside the brackets you can see the function f and its derivatives evaluated at the endpoints, in addition to the exponential evaluated at the endpoints. Okay. This result can be generalized to generalized Fourier integrals, in which you have a function phi in the exponent by simple change of variables. So this kind of approach, the integration by parts, covers also this kind of integrals. Just to give you an example, here you have the integral from 0 to 1, which is whose integrand is the exponential, the Fourier exponential divided by 1 plus t, which is a function regular inside the integration domain, because this function would have a simple pole at t equal -1, which is outside the integration domain. When k tends to infinity, we can integrate by parts, and we find what is written here at the bottom, which is an asymptotic representation valid up to an arbitrary n. Here it is truncated to some n, again in the limit when k is large. When the function f is instead singular, we may resort to some generalized Watson's lemma. So it's a Watson's lemma valid for Fourier integrals. It's not exactly equal to Watson's lemma valid for Laplace integrals, because in this case we have the following assumption. The function f must be 0 with all its derivatives at the upper integration limit, t equal b. So whereas in the Laplace method we are free to change the upper integration limit, and we don't care about the upper integration limit, and we don't care to the behavior of the integrand close to the upper integration limit. Here we must assume that the function is negligible along with all its derivatives at the upper integration limit, just to isolate the contribution from the lower integration limit, which is 0. Now we will assume that the function exists with all its derivatives in the integration domain from 0 to b, with the exception of the endpoint 0, and that in a neighborhood of this endpoint, the following asymptotics holds. So our function f can be approximated by a power of t with the exponent gamma. Okay. Now, if all this is true, then we are able to get this asymptotic representation of the integral, in which you can see there is an inverse power of k up to gamma plus 1. Then there are numerical constants, in particular, again, the gamma function, which is ubiquitous in asymptotics, evaluated at gamma plus 1. And then there is an exponential in which you can see all the involved constants. The main difference between this form of Watson's lemma and the one valid for Laplace integrals is that in this case we don't have a complete asymptotic expansion. We only have the first order term, the dominant term in the asymptotic expansion. So you don't see here a summation. You only have this contribution and no others. Now, if the function phi has instead an internal stationary point, the procedure is exactly the same as in Laplace method. So what we do is a Taylor expansion, a truncated Taylor expansion of everything is involved. So in particular, the function f will be evaluated at the minimum point, C, whereas the function phi will be expanded using Taylor series up to the second order again. If you do that and you change integration variables, so you introduce a new variable tau, which is related to the old variable t in this way, where mu is the sign of the second derivative of the function phi at the point C. Well, if you change variables, you will discover that your integral becomes this integral here, in which you get a simple exponential function, e to my 2 plus j mu tau squared. The integration limits depend on r, but they can be let tend to infinity without changing the asymptotics. Since we know the value of this integral when the integration domain has been extended to infinity, then plug in everything inside the expression here, you will get this final formula, which is very similar to the final formula of the Laplace method, in which you can see we have the function f evaluated at C. We have the exponential, the Fourier exponential, also evaluated at C. And then we have this term here, which is the algebraic term in the asymptotics, where again k is in the denominator and inside the square root. So the pattern is more or less similar. Here, everything is written more formally. So if we have that C is the only point inside the integration domain where the function phi vanishes, if the function f vanishes infinitely smoothly at the two endpoints, A and B, and if the functions f and phi are infinitely differentiable on the half-open intervals on the left and on the right of the point C, if we know the asymptotics of the function phi in the neighborhood of C and of the function f in the neighborhood of C again, where in those asymptotics, asymptotic representations, some constants are involved. They are alpha here and beta there. And in particular, in the function phi here, you have the second order term of the Taylor expansion, whereas in the function f, you may have a general exponent gamma, as in Watson's lemma. Then, if the exponent is larger than -1, so that the integral is well defined, the following formula holds for the asymptotics of our Fourier generalized Fourier integral, in which you can see this looks like a bit complicated, but it's not so complicated after all. The important parts are the exponential here, which is a phase, which is the Fourier exponential evaluated at C. Then there are a bunch of constants, beta, the gamma function, the exponential function here. And then the other important term is the one where the large parameter is present in the denominator. This is an algebraic term whose exponent is gamma plus 1 over 2. Okay, so this is the formula for the stationary phase method to the lowest order. And also in this case, we can generalize this. For example, we may allow the function phi and f to have different asymptotic behaviors on the left and on the right of the stationary point. So we introduce constants alpha plus, beta plus, and alpha minus, beta minus, and so on. Everything is generalized quite smoothly. No particular changes. To give you an example with which we will finish our discussion, we can evaluate, which is a practical example, we may wish to evaluate the Bessel function of the first kind, J, whose order is n and whose argument is also n, in the limit when n goes to infinity. Now, to do that, we need some representation of the Bessel function, which may be defined, as you may know, in a number of ways. For example, as the sum of a power series, also as a contour integral in the complex plane. One of the integral representations on the real axis is the one we will use here. That's an integral from 0 to pi of a simple cosine function. However, the argument of the cosine involves another trigonometric function, which is the sine. And so this integral cannot be closed analytically. It can be written in terms of exponentials by writing the cosine function as the real part of an exponential, in which you see the large parameter n is factored in the exponent. And here, the function sine of t minus t is represented close to the origin through its Taylor series, like by expanding the sine function as t minus t to the third power over 6 plus higher order terms. If you do that, the t term here is cancelled by this t term there, and you end up with an exponential in which in the exponent you only have the term t to the third power over 6. Now, this exponential here can be evaluated asymptotically by expanding the integration limit, and again you will get a gamma function. So in the end, you will discover that up to a bunch of constants, numerical constants, including the gamma function, our Bessel function with the order equal to the argument goes asymptotically as the inverse of n to 1 over 3, which is something quite unpredictable from the beginning. Okay. And we have simply applied the general formula here by letting the constants, the involved constants, have the values appropriate for this particular example. For example, alpha plus is equal to minus 1 over 6 because of this Taylor representation in the exponent. Beta plus is equal to 1 and gamma equal to 0 because the function f is simply a constant. Okay, the final remark is a comparison between the Fourier and Laplace methods. The Fourier method is able to give us, through the stationary point approach, and the dominant contribution to the exponential, to the asymptotics of our integral. However, if we need also the next terms in the asymptotics, then we also need to consider the endpoints, because the endpoint contribution is not exponentially smaller than the stationary point contribution, but it's only algebraically smaller. And so it contributes to the higher order terms in the asymptotics. In contrast, Laplace-type integrals have the advantage that you will get the entire asymptotic expansion from the behavior in a neighborhood of the minimum of your exponential function. So you don't need to care about endpoints. And this is the reason why the Laplace method is more powerful, and it constitutes the basis of its generalization, if we may define it, a generalization of the Laplace method in the complex plane, which is known as the saddle point method or the steepest descent method. And that generalization is sufficiently more complex that we will discuss it in a separate lesson, which will be the next one. Okay, so it's everything for today. Thank you for your attention. Again, I'm following more or less the contents of Ablowitz and Focus on this part on asymptotics. If you wish to go more in depth on these topics, you can start with this book, and there are also many others. Thank you.
Thank you. Good day.
Thank you, Annika. Thank you, everybody. Also Alvaro and Antonino. See you on Thursday.
See you. Bye-bye.